In the end, where do I want to take it? What do I want to get out of it? A high image, right? I took the projection. And I want to take all the projections that I took and return them back to an image. So it's called back projection. The projections that I took and returned to the image are called back projection. When all these projections are gathered together, what do they create for me? It's a bit annoying or tricky, but just to make it clear, to explain further, let's say this is the origin, and in a more detailed manner, that's it for better understanding. A solid material has very high attenuation. And I took a projection here, and I took a projection here, and I took a projection here, and I took a projection here. All right? So we can say that the projection I took has its data stored here in this area, and it appears like this. Each one of them sees the object in the same shape from their angle, right? Every view, every projection I have, every projection of mine. So, the image he wants to create is empty. These are the projections I took. Now, what does he want to do? This place has specific dimensions for him, which he calls X, Y, and Z. These dimensions are where the object is located, X, Y, and Z. So what does he do? He starts to tell you that he doesn't know if the attenuation comes from this point, that point, or this point. The object could be here, here, or here. He doesn't know. It could be here, here, or here on this side as well. The same goes for this side. It could be here. Why? Because the X section in the center is the only one that is certain, right? You don't know exactly where it is. So, he starts to do something called back projection. What is back projection? It comes to the image and does what? He starts by saying, I will place each one of them to contribute their data. This first one will say, okay, throughout my path, I will place my data in this way. So he arranges his data like this, placing it in this track. The second man, or the other projection with me, is quite a lot. He placed his data on the entire track along its path. Everything is fine. Now let's assume the angle is set so that the colors look good. We will take the fourth projection using a completely different angle. What is the area where you see the data concentrated? Ah, you got it, the center. That's correct. But there is data at the edges, right? What I did is called back projection. What is it called? Back projection. Now I want to remove the data at the edges. So I will do something called filtering. I named it filtered back projection. This filtering removes the excess distant data as if it's doing filtering. So when filtering is applied, who will remain illuminated? The center, right? So the original image will be restored. Correct. Okay, let's see this mathematically. I have about 800,000 projections happening in the 60 to produce a 512 by 512 matrix, which is 12 by 512 in matrix terms. Of course, if we assume that you all understand this, the topic will be difficult. Here is my object that I am talking about, and here are my projections taken from all my angles. Each one of them should start to drop their data onto their track. The data on the track, the most illuminated part, which is this section, is the back projection. Now, apply filtering and remove all the unnecessary things. So I will only have the illuminated part, which is where my object is. Now, let's see how this is done mathematically. Let's assume that my image of the human body is represented as a matrix, a 2x2 image, meaning 2 rows and 2 columns, which are A, B, C, and D. The first angle you take collects the data of A plus B, which is A plus B, and the second angle collects C plus D. This angle only sees the annotations of C and D, and this angle only sees A and B. Now, take a new oblique angle. It will see B and A, while D will see C. Take the third angle, B plus D plus C. Now take the fourth angle, D plus B plus C. What I did here is called projection. I have now obtained my projection. These four, or A and B, are essentially the ones present in the patient's body, and it's as if I am viewing them from different angles or different views. This is the image I have on the machine where I want to place the data I collected. The data I collected, I want to input it into this matrix. Here is the data I gathered from all my projections. So I will input A plus B here and here, and input C plus D here and here, and input B here, and input A plus D here and here, and input C here. So each one returns in the track. Here it returns A plus B, A plus B, C plus D, C plus D. Now return this. B added to A plus D, A plus D added to C here. Return the third. B plus D, A plus C. Return the fourth. So, what is this black thing? It's B plus C. And it came back here, and it came back here, and here it is again. So, you did back projection, but the image has a lot of data, which we were talking about earlier. What do you do next? It's filtering. Filtering is fine. It's a mathematical thing. So, what does it do? For example, it presents values, for example, from each pixel, meaning it subtracts A plus B plus C plus D from each pixel I have. So I end up with triple A, triple B, triple C, triple D. Then, for example, these values are divided by 3, meaning the first pixel is divided by something. Or the first pixel, for instance, had 2 A's removed, and the second had 2 B's removed. The image here is returned. Now let's understand this part with numbers, because you won't grasp it with A, B, C, and D. I want you all to apply what we talked about earlier. Here is the image, and here is the data present in the image inside the patient's body, inside the marine. Take the first one. It will give you 3. It will give you something. That's a lot. 7. Okay, let's take it again. How much did this give me? 2, 5, 3. Come on. 6, 4, 4, 5, 1. Is that okay? All right. This is my image, and this is the data that I collected. I want to return the data. What should I do? Where will the 3 go? Here and here. Where will the 7 go? Here and here. The 2 is now here. The 5 is here and here. The 3 is here. 3 and 3 make 7, and 7. Returns to 2 on 3, leaving 5. 5 on 7 becomes 12. 5 on 3, and forget it. So he keeps adding, keeps adding. What will he do with everything he adds? He said, subtract 10 from everything, and it returns to 3, 6, 9, 12. Okay, we're done. No, he said, divide by 3. 1, 2, 3, 4. What is this? 1, 2, 3, 4? Isn't this our foundation? The foundation that was the first segment in the structure of the skin. We take the projection, perform back projection, and apply filtering. The filtering will ultimately lead you to the original image, which is in 1, 2, 3, 4D, your image. After the projection and back projection, we finally reached color 2, 3, 4. Do you understand? This is the filter back projection technique, which is commonly used in various applications, in all cases. Well, today's discussion does not use filter back projection. It exists as a standard, but is replaced by another type of reconstruction algorithm called iteration, or iterative reconstruction algorithm. The advantage of iterative filter back projection is that it is easy and does not take much time in processing. The time it takes for calculations is not significant. However, the iteration has become something better and more complex, but it shows better results. Why does it show better results? It shows better results with things that have low dose, meaning things that contain noise or images that are poor, and you want to improve their image quality. You use the iterator. In fact, all companies today have iterative technology. For example, if you are working on a Philips device, you will find something called AI 3D. And if you are working on a Toshiba machine, you will find something called AI 3D. If you are working on, for example, the metal artifact reduction software, which removes metal artifacts and relies on the iteration reconstruction algorithm, everyone today is racing towards the idea of iteration. So, what is iteration in its concept and meaning? It depends on the iteration. Today, everyone is competing in the idea of iteration. So, what is iteration in its concept and meaning? The first stage of it is the projection stage, which will be exactly the same. However, it creates a phantom image in the control. This image is called the estimated image. This image is created on the machine itself, and what it does is it performs an image quality assessment to achieve the optimum quality. Then it starts performing a series of mathematical operations called iteration. These mathematical operations begin to work on the projections it has taken and compare them with the estimated image until it reaches a quality level that matches the image quality it has. In this case, we accept the image. To visualize what is happening, here is our image that exists in the batch. It takes projections. We haven't changed anything. The data it has taken is now averaged, meaning 3 and 3, 6 and 6, 4 and 10. The data it has gathered from all this, which totals 10, creates an image. This image contains values, where each pixel has an average value of 2.5, 2.5, 2.5, 2.5. Is that clear? Lessons from NOV. Is that clear? Okay? Then it starts to do something called the correction factor. The correction factor acts as a correction coefficient for the image quality. For example, if you have an image with high and low pixel values, what do? You perform averaging to see what each pixel is next to. You take the average of all these pixels, so the resulting image will be very smoothed and nice. This is exactly what it did. It uses a specific method called C11 for the correction factor, subtracting this from that, dividing by 2, and subtracting, for example, this from that, and dividing by 2. Subtract this from that and divide by 2. From this, it calculates a certain value called the correction factor. This means taking the first row with the first column of the incoming data and the first row with the estimated image that was created here, which is 5. Then it subtracts the data from the first column of the estimated image, which is the smoothed image, and divides by 2 to give you the final correction factor. This correction factor is used as a correction factor. It adds or subtracts from the original image or multiplies it with the original image, which is called the multiplication method or the additive method, until it reaches this point. It creates a correction factor, takes the correction factor, and applies it to another image, resulting in a new image with enhanced values. These new values have undergone some enhancement or improvement, and it compares them to the estimated image. When it comes to comparing With the estimated image, it says, yes, the image quality is acceptable for me. You then input the values of the process being performed, which involves multiplying it with the original image to produce a new image. The more you increase the adjustments you are making, the better the results will be. It takes longer on the computer for the mathematics that are processed. The more you increase the iterations, the more you will find that the noise in the image starts to be significantly reduced, and you will indeed see that the image has become noticeably much better. The concept of iteration in general, I don't want to go into details, as there are many details that you might be unfamiliar with, but I believe the picture is quite clear to you, right? Are you ready? No? Who are you, Dr. Hani? No, I'm just fine. But another thing, right now we have understood that we took the projection of your image. Okay? This is the one inside Bisha. Normally you take a projection here, a projection there, a projection here, and a projection there. Is that clear? Is there a problem with this so far? Very good. The average will be taken for all the data present in the image. I have 1, 2, 3, 4. What is the average? It's 2.5. This means you add them up, for example, and divide by their count, which will give you 2.5. It will create an image with the same number of pixels that this image has. And it will set its value to 2.5, 2.5, 2.5, 2.5. Is that clear? And this image takes a projection here, and takes a projection here, and takes a projection here, and takes a projection here, with every row and every pen present. Right? Right? This image is what? Or it will be built upon. This is his model. This is the estimated image, the image he created and produced from the data he collected, and I want to reach this quality. Get it? Okay, what does he do to get close to this image? He essentially calculates the correction factor. How does he do that? Each row here, he basically takes this row and subtracts the 2 and divides by 2. This column has a value of 4. 4 minus 5 divided by 2. The second one is 7. 7 minus 5. All right, so I'm essentially working on this, meaning I will work on row and column, this with this, and this with this. So in this case, what do? You essentially calculate the correction factor, which is C11. So it's 3 minus 5 over 2, 4 minus 5 over 2. What's the value? 1.5. He takes this value and substitutes it in the data. What does 2.5 become for you? When you subtract minus 1.5, what does it become? It becomes minus half. So the 2 changes, 2.5 becomes 3, 2.5 becomes 4. It's as if he's essentially adding it for you, and it goes back to your original image. Clearer now. When you don't have the original image, how will you obtain the original image? The detector brings it, but how will it place this detector on the pixel? This is not easy. We need to talk about 800,000 designs of the subject. This is the subject I'm discussing. It costs $100,000. How will this data be placed? This is what I will tell you. I will explain it to you simply. But if we delve into this discussion, it becomes a long story. However, I am trying to help you understand what iterative means, just so you can grasp the topic and the definition when you read it. Now, if you don't like this image, you can manage another one. The new one that came out compares these 1, 2, 3, 4 with 2.5, 2.5, 2.5. If the first image doesn't satisfy you, perform a new iteration on the order of the iteration to get a new correction factor and so on. But we don't want to dwell on this part, of course. The choice of iteration is up to the user. But who does it? Of course, the computer does it whenever you do. What is the benefit of removing your voice? It is useful in situations that contain high volume or noise. This topic is present, for example, in Siemens and Toshiba. These are the names found on the devices. For instance, you might find names like Sapphire or Iris in Siemens or Toshiba, such as the AI 3D, Adaptive Iterative Dose Reduction, or GE's devices, or the MPIR or Philips devices. This information is available globally. Fourth generation of iterative reconstruction. 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 So you are giving a very low dose, and the image quality is obviously not something all users working on the machine are aware of. This is another problem. The applicator itself, with all due respect, is not the same for everyone. This requires attention. For example, in images like this, you can see the noise in the area I have, which is always present. If you take a picture of yourself, you can see how the noise looks here. For example, the image has improved like this with a different generation. The filter back projection quality has changed. Here, the noise has started to decrease with the same dose. There are many recipes on this topic. Here they are. I said, also, the city number means that there should be a difference in the city number. If the city number is obtained and there is noise and artifact, the city number will be valid. It would be a mistake. Therefore, removing this artifact is very, very, very important in the iterative process to reach the correct city number that exists. Your correct city number that exists. This is the name of the commercial one. I showed the image episode. These are the commercial names. But the options will also be launched on the device. People are supposed to switch to the iterative one. Of course, now everyone is talking about the iterative techniques. I mean, that's it. It is very important in dose reduction and very important in image quality. For example, improving spatial resolution and improving the contrast to noise ratio. I know this material is not really within the scope or the main topic, but you might want to take a look at it to understand how the story is going or how the publications are discussing it. Image quality, resolution, noise, and contrast. Of course, we talked before about resolution and special resolution. If I have two objects like this, what do you think is a significant factor for me in resolution in the context we are discussing? What is the most important thing I am talking about in CT, computed tomography? It could be the detector size. If the detector size is large, do you think the resolution will decrease? So, the detector size is a significant factor in the topic of resolution. In special resolution, I have something called special resolution and something called temporal resolution, which we have discussed before. Special resolution means if I have two objects with a space between them, but you have a large detector size, it won't be able to see the gap that exists. The detector size should be small, so that there is one device and another device, and one device can see all three devices like this image. Therefore, the detector size is one of the very important factors in determining resolution. If we remember the topic of MTF, modulation transfer function, the same applies to determining special resolution in terms of line pairs per cm. In CT, it is usually 20 line pairs per cm in this range. The same applies to determining special resolution in terms of line pairs per cm in CT, which is usually 20 line pairs per Siemens. Per centimeter, I can see up to 20 line pairs per mm. And of course, it is measured, as we discussed earlier, using the phantom that contains your line pairs. Now, regarding resolution, I have two aspects. There is resolution in transaxial resolution and resolution in the Z direction. Is it I am taking a cross section or a slice regarding this section along the axis of the section itself, which is the X or X axis. This is in terms of resolution in that direction, and resolution for this section and the section after it and the section after that, which are now in the Z direction. So now I have two resolutions. Resolution in transaxial resolution and resolution in the Z direction, which I call Z sensitivity. As for the transaxial resolution, it is in the range of 7 line pairs per sem. This, of course, varies depending on the manufacturer and the machine. Some machines will tell you 20 line pairs, others 15, and some 10. This varies based on the company and its credibility, because you might perform a measurement with a phantom and find that the resolution stated in the specification is not accurate. This happens, so it must be measured, and it should be measured by a medical physicist